Good afternoon. My name is Paul Sabanal, and this is Mark Yason. We both work for IBM ISS X-Force. Today we're going to talk about reversing C++ applications. Okay. Reversing C++ is notorious to be very hard to do and tedious and time-consuming. Our main motivation for this talk is the general lack of publicly available information regarding this subject. As reversers, our day-to-day job involves analyzing malware and analyzing vulnerabilities. And nowadays, use of C++ code in malware are increasing. The more famous examples would be Agabot and MITRE variants. So as reversers, we have to know how to reverse malware compiled in C++ to be able to do our job effectively. At the same time, the most modern applications nowadays use C++. So if you're doing binary auditing or you're doing vulnerability analysis, you have to know how to reverse C++ to be effective. In this talk, the purpose of this talk is to understand C++ concepts as they appear in the disassembly, and to have a big picture idea on what the major pieces of the classes or the major pieces of the C++ target and how these pieces relate together. In this talk, we will focus on identifying classes, identifying the relationships between classes, and identifying the class members. Oops, please wait a minute. Apparently I opened the wrong slide, so I have to open another one. Sorry about that. It's an old version. Okay. Okay. We're not going to discuss the more obscure C++ features, since when we're doing this, even these three is hard enough to do or hard enough to analyze. So we are going to reserve that for a future talk, maybe. Also, please note that we're only going to discuss the Microsoft Visual C++ compiler. Other compilers, such as GCC, would have different implementation, but since they are compiling the same language, obviously, there will be some similarities. So we believe that it will also help you. This talk will also help you in doing reversing of GCC compiled C++ binaries. First, we're going to discuss the manual approach, and then we're going to discuss how to automate the tedious task related to this activity.
So the first thing you'll need to do is to identify if the binary is a C++ compiled binary. So when you load compile the C++ binary in EdaPro, you see a heavy use of ECX. So ECX is used as a disk pointer. So, for example, in the first example, you will see a parameter being pushed in the stack, and ECX is initialized with a specific value. So another thing you can look at is the function. As you can see in the entry of the function, ECX is used before a value is stored in it. So in this particular example, so it moved the value of ECX, which contains the disk pointer, and then probably try to specify the virtual function table as the first D word, and then on the second D word, the second D word is probably a variable. So like before, ECX will be the parameters on the stack. The parameters are passed on the stack, and the ECX pointer will have the this pointer. So this is an example of an indirect function call. As you will see, it will first create an object using new, and then put it in EAX. And then what it will do next is to get the first D word, and then try to call the first D word pointed by this pointer, which points to the virtual function table. So another thing to look at is if on a compiled C++ binary, you will see that you will recognize that some STL code and some like this one, which uses the basic streambuff class.
Okay, one of the most important things that you have to know when reversing C++ applications is how the object is laid out in memory, or its class instance layout. With your own programs, you can actually see how the classes that you make are laid out by using the -d1 report all class layout switch for cl.exe to dump the layout in SCDS into the standard output. So in this example, I have here a class x1. This is a very simple class. It has 3 member variables and 1 non-virtual function. So how would this appear in memory? As you can see, it only stores its 3 member variables, with the last one being a character type. It will be a padding will be added to align it. And for classes that contain virtual functions, a virtual function table pointer will be added before the class members in the layout. The virtual function table pointer points to the address of the virtual function table. In this case, since we have 2 virtual function get sum reset values, and they will appear as they were in the order they are declared in the class declaration. So what if the class inherits from another class, from one class? In this example, the class x3 inherits from the class in the previous slide, x2. Class x3 has 1 member variable. So what actually will happen is that if you inherit from another class, its class instance will be embedded into the derived class instance, and it will be placed before the derived class own instance data. So as you can see, the previous layout that I showed for x2 is embedded before var2 in x3's instance layout. If a class inherits from more than one class, this will happen. In this case, we have class x5, which inherits from class x2 and class x4. So as you might have guessed, the same thing happens. The base classes, class instance data are embedded inside the class x5's class instance layout. If you may have noticed, class x5's virtual function table pointer is not present. And that's because there's a rule that if there's no virtual function table for the virtual function table is only added to the derived class if there is no virtual function in the base classes. And you also notice that func1 in x5 overrides class x4's func1. So what will happen in the virtual function table? Okay, here's the virtual function table for x5. As you can see in the second group, what's supposed to be X4's func1 was replaced by the pointer to X5's func1. Now, please remember this layout because it's very important when analyzing in the later discussions. Now, how do we identify the classes? Our manual approach entails we first search for constructors, and we assume initially that each constructor corresponds to one class. Of course, it's not always true because a constructor can be overloaded. So there could be more than one constructor for a particular class. But initially, we don't have to worry about that. We can correlate that later by seeing if several classes has common member functions. If they have, it is probably an overloaded. It is probably the same class with an overloaded constructor. So, to be able to identify to be able to look for constructors, we have to know how objects are instantiated. There are three common types of objects in C++. One's global object, and the local objects or the stack objects, and dynamically allocated objects. For the global objects, these objects are declared as global variables, and they are allocated like all global variables in the data segment of the program. The constructor for global objects are called at program startup, and the destructor is called program exit. One way to find the constructor and the destructor for a global object is to identify parameters to these functions, underscore C init and underscore at exit. Here's an example of global object. And here you have to analyze cross references to where the global variable is stored in the data segment to be able to look for the constructor. Now, local objects, on the other hand, are allocated in the stack. The constructor is called upon the declaration using an initialized stack variable as a dispointer. You have to look for the constructor. Look for load to ECX using a stack variable as a source, that stack variable has to be used for the first time at that point. It has to be empty. The destructor is implicitly called when object is out of scope. For example, if you declare an object inside an if clause, once you exit that clause, automatically that object will be destroyed. And or for example, if you're inside a loop, you declare an object inside a loop. When you get out of the loop, the object will be automatically destroyed. Here's an example of that in the disassembly. This is actually an if statement, and the block begins over. In the first red line, the constructor for that object is called. Notice that before that line, EBP var8 is used for the first time without even being initialized, and it's loaded in ECX. So that's a clue. There's a clue that this is a possible constructor. And notice that at the end of the block, where the if statement would end, you'll notice there's a call to another function using this pointer, the same value in ECX with the one declared in the constructor. And this indicates that this is the destructor because it's the last one called at the end of the scope. Now, dynamically allocated objects, on the other hand, are allocated in the heap, and they are created by the operator new. The operator new has a parameter is passed the size of the object as parameter. So that's another clue that we can use later on to give us a clue on how the objects are laid out. The object size is very important. And the returned value by new is used as the dispointer for the constructor. The destructor, on the other hand, is called via operator delete. This has to be explicitly called, so it can be called anywhere. But it's not always true, because there are some mechanism actually in C++ where you can declare the dynamically allocated object that will be automatically destroyed using the auto-PDR keywords. Here's an example of a dynamically allocated object. As you can see, the first red line is a call to operator new. And the parameter passed is 4, so the size of the object is 4 bytes. Further down on the second red line, you can see the call using the return value operator new as a dispointer. So that is a clue, that is possible constructor. And on the third red line, actually also uses the same this pointer, but you actually will not know exact 100% if this is a destructor or not. But you can see that below that there's a free call, so you can see that the object is being deallocated at the point. So that's another clue. And you can possibly say that that function is a destructor. Okay.
So another method for identifying classes is via the RTTI. So it is used for identification of object type on runtime. It is generated for polymorphic classes or classes with virtual functions. Basically, RTTI is used by the operators type ID and dynamic cast. RTTI will give us information on class name and class hierarchy, so it has pretty good information that will give us a rough idea of what the class is. So it consists of several data structures. So the first data structure for RTTI is what we call a RTTI complete object locator. It has a pointer to another two data structure. The first data structure is called the type descriptor. It will contain information about the class, like the class name. And the second structure is the RTTI class hierarchy descriptor. It will contain the hierarchy of the class. So finding the RTTI involves finding a VF table. So you will see when you load a sample in Nida, you will see several pointers throughout the code. And if you look one D word before, if you see a pointer to what looks like a data structure, then probably it is an RTTI complete object locator. So this is the data structure of the RTTI complete object locator. At offset C, it contains the type descriptor, which contains the information about the class, and the offset hex 10 will contain the class hierarchy information. So it is what it looks like in this assembly. So put in mind that this one is already pre-processed, so we already modified the variable names. So the type descriptor basically contains the important class name. So if the class of RTTI and then the class name exactly describe what the class for, then you will have a rough idea what the class is for. For in this example, if the type descriptor says the class name is C packet parser. So it probably means that the class is a packet for a packet parsing. So the class name is Mango. It has the class name is in between a dot and then a question mark and then AV, and then the class name and then two at sign. So this is how the class hierarchy descriptor looks like. So the attributes field contains information if it's multiple inheritance or virtual inheritance. So it contains the number of base classes, how many base classes the class has, and then it contains an array of data structure for each base class called the base class array. So this is an example. The number of base classes here is 3. In this example, class G is inheriting from class A and class E. So the number of base classes here is 3, including itself. So you just decrement by 1. And then the P base class array points to an array of RTTI base class descriptor, which will be discussed later. So this is the base class descriptor. So each base class descriptor, each base class descriptor will contain a type descriptor for that base class, and then it contains the VF table offset. It will also contain the VB table, which we'll discuss on the next slide. So the VB table is used for multiple virtual inheritance, in which you will need to up class to a specific class. So in this example, class G is inheriting from class A and class E. So what is the mechanism for C++ to specifically type class, to specifically up class to class A and class E? So what is used, the class base class descriptor has this pdisp field, which contains the offset of the v table. So it points to 4, which is that 4, and then the VB pointer points to the VB table. So that is the VB table. And if you look at the vdisp field, it contains 8, which means that it points to the third D word inside the VB table. So you will just need to add 16 and the offset of the VB table. So you will have 20. So that 20 is the actual offset of class E inside class G. So this is what it look like in a graphical view. So there are the classes and then the VF table. So before the VF table, which a pointer to the complete object locator. The complete object locator will then point to the type descriptors, and then the complete object locator also points to the class hierarchy descriptor, which will then point to a base class descriptors, which will then point to the type descriptor of each base class.
Okay. Now that we have identified the classes, it's time to identify the relationships between them. To do that, one thing we could do is to analyze the constructor for each class. Constructors contain very important information, such as the base classes, because the constructor will implicitly call the constructors for their base classes. It is responsible for initializing its base classes. Another important information is the location of the virtual function table. The constructor is also responsible for initializing. Remember that class instance layout earlier? There's the the virtual function table pointer field. The constructor is responsible for loading the address of the virtual function table in that field. So you can actually get that information from the constructor. And another thing is that member variables are almost always initialized inside the constructor because that's the purpose of the constructor. You initialize the object. So normally if you program C++, you do most of your member initializations inside the constructor. So you can get most of the info about the member variables inside the constructor. Okay. So how do you identify classes that inherits from another class or single inheritance? You can do that by looking for a call to a constructor that uses the same this pointer that was passed into that constructor. We already know that this function is a constructor. But inside the constructor, there's a call to a function using the same this pointer that was passed to the current constructor. This could possibly be a constructor for a base class. However, we have a little problem here. It looks exactly the same as when you call a member function of this class. So how do we distinguish whether this is a call to a base constructor for a base class or simply a call to one of its member function? Actually, there's no sure way to know that other than looking at the function, the called function itself, and see if it is instantiated somewhere as a class of its own, or see if it's used somewhere else as a base class using the next example in here. Multiple inheritance actually is much easier to identify or much accurately identified because the first base class is the same. It looks the same with the previous example in the single inheritance example. You can't identify really if it is a base class constructor or a call to a member function. However, the second base class is different. Actually, this pointer is changed to point to remember the class instance layout where the class instance data for that base class starts. That is actually used as this pointer in this case. So here's the actual class instance layout for the previous example. As you can see, the base class B instance data appears in the offset 4 of class C's instance layout. And you can see here, it adds an a 4 to ECX. So we are almost sure that this is a call to a base class. And since the one above the call above it, which we are not sure if it's a call to a constructor or call to a member function, is called above it. Since this is a compiler-generated code, we can say that the previous call is also a call to another constructor. So we can safely assume that this particular class inherits from 2 base classes.
So for polymorphic classes, it is easy to identify the base classes because of the RTTI base class descriptors. So again, this is the class hierarchy descriptor for a specific class. So it will contain the number of base classes and pointer to the array of each base class for the base class descriptors. So here's an example. So to determine the basis for class C, you will just need to follow the VF table related to the class, and then find the complete object locator. and then follow the class hierarchy descriptor, and then follow the base class descriptors, and then each base class descriptor points to the base class.
Okay. Next, we're going to discuss about identifying class members. To identify virtual functions, we have to get the virtual function table. And we can do that through constructor analysis. This is the code for a constructor. And as you can see, in the highlighted line, there's a move instruction wherein an address is copied to the first field in the class instance layout. And below that, there's also another one that is copied into offset 14 relative to the start of the class instance layout. Now, what this means is that, and if you look at the address, we can see that it contains function pointers. Of course, you have to look at the function first to know that. And you can see that there are several functions in there, and that would give us a clue onto what this is. But most of the time, this will indicate that that these addresses that were copied into the instance data layout fields are the addresses of the virtual function tables. And also note that there's another important info that we can get here, EDX plus 14. It will help us indicate the size of the previous instance of the previous base class above it. So it's 14H. It can be useful at some places. Now, here's an example of a virtual function call. Okay, the ECX, the pointer in that virtual function table pointer field is put inside EDX, and 4 is added to EDX, and that indicates that the address of the second virtual function, and then there's a call to EAX. So how do we identify non-virtual member functions? We can identify these by looking for function calls where right before it ECX is loaded with this pointer, but you can't. It's not it's not 100% sure. So you also first have to look inside the function and see if the ECX that was copied before is used but not initialized or not being overwritten. In that case, we are sure that this particular function is a member of the class where this pointer points to. Now, identifying class member variable. This one is actually easy. We can see here that this pointer ECX is copied to EAX, and a value is being written to it. So you can see that there's an access into the particular offset in the class instance layout. So that would give us a clue that this is offset 8 of that class instance layout is a member variable. Now, we can do all that, identifying the classes, class relationships, and the class members, but it is a very tedious and a very time-consuming task. So we did some automation of the particularly time-consuming task. It's not 100% perfect, but if we seek for perfection, we won't actually get done. So what we did was first we developed a tool in either Python. And then when the Sabre Security released IDA2SQL, the script that imports info from the IDB and more to a SQL server, we wrote the code in Ruby. And we'll show you a demo later. And here, why static approach? We are doing static approach because we are planning to support other platforms as well that are hard, where it's hard to do runtime analysis like Symbian. But of course, a hybrid approach may or will produce more exact results. Okay, here are some of the strategies that we use. It's good if you have RTTI info, but if not, when RTTI is not available, we resort to some heuristics to identify, to do the automation.
So the first thing that a tool can do is try to leverage RTTI if it exists. So with RTTI, you can identify the polymorphic classes, the class names, the class hierarchy, and the virtual function table and virtual functions, and the destructors and constructors of polymorphic classes. So the first thing you can do is to try to enumerate each item and in each item in the disassembly. If you can identify if for VF table, if an item is a D word, and then the item is a pointer to a code, if it tries to point to a code. And if the item is referenced by a code, so it means that that this particular D word item is used for as a VF table assignment. So as I said before, the RTTI complete object locator is just below the VF table. So once you have the BF table, you will need to identify if RTTI complete object locator exists. What we try to do is try to parse the RTTI complete object locator, and then try to determine if the type descriptor it points to is valid by checking for that question mark AV prefix for the class name. And then once you did that, you will generate a new class, and then you will put the class name from the type descriptor, and then you will have the VF tables, and from the VF table you will have the virtual functions. And then the constructors and destructors can be identified for all the functions that is referencing the virtual function table. And of course, you will have the base class from the class hierarchy descriptor. So what will happen if you don't have an RTTI? So you will only have the BF table and then the base classes are not identified yet. So class names can be automatically generated. So from functions referencing the BF table, you still don't know if the particular function is a constructor or destructor. You can try using some heuristics to identify, to segregate constructors from destructors. One of them, if the particular functions is being referenced to by a jump instruction or a call referencing to the functions, and two instructions before that has the following form: a move and then a -1, and then LEA and then ECX. So once you have that, you can just cross out the CTORs and DTORs. You will have you had segregated that into constructors and then destructors.
To be able to do what I'm going to explain later, we devised an algorithm. It's actually graph-based. It's a very simple data flow analysis algorithm. I don't even know if you can call it data flow analysis. But what we do here is we start from a certain instruction, and we have what I call a track variable, which is the initial register or variable wherein the value you want to follow is in. And whenever it is copied, you just split the branch and follow and do the same thing with the other branch. Follow the value and until that particular value is gone or overwritten. So basically, this is a graph wherein every node represents lines of code where the track variable contains the value that we initially tracked when we start the graph. So this is useful in some cases. Actually, this is loosely based on a code by Halver. I think it's from x86 RLib. I think you should check it out because there's a lot of interesting code in there. To automate constructor identification, we do the following. First, for dynamically allocated objects, we look for calls to the new operator, and we track the value returned in EAX. We use the algorithm I described earlier to track the value returned in EAX. When tracking is done, we look for the earliest call where the track register or variable is ECX, and we mark this function as constructor. Now, most of the time, the function found is simply a few instructions below the value returned in EAX, so this is probably overkill. But for the next one, for local objects, we do the same thing, but instead of initially tracking returned values of new, we first locate instructions where an address of an initialized stack variable is stored in ECX, then start tracking ECX. And then when tracking is done, we look for the earliest call where the track variable is ECX and mark this function as the constructor. In most cases, this will actually work. So after constructor searching, we'll have the following information added to all that information we gathered previously. That's the nucleus constructors, which are the identified constructors. Now, inheritance identification. How do we do this? For each constructor, we track the this pointer or the ECX from the start of the constructor. We track it, and when it's done, we check blocks with ECX as struct variable. That means that ECX contains the value, the original value of ECX at the start of that function, and we see if there's a call to a function in that block. If there is, this is a possible constructor of a base class. But we still have to check, like I mentioned before during the single inheritance explanation, we have to do an additional check if this is really a base constructor or merely a member function. And another one is we check the block and see if an offset is added to ECX. This is done to check for another base class, which is being initialized by adding by modifying this pointer. So if there is, we check that new ECX, and we do the same thing we did with the constructor searching algorithm. We look for the earliest call with ECX as a track variable, and if we see one, it is a possible base class constructor. After inheritance identification, we'll have the following info added. We have base classes. Now, how do we identify member variables? To do this, we track the this pointer from several locations. One is the point the object was instantiated, and one is the beginning of the constructors, and another place is the beginning of member functions. And then we note accesses to offsets relative to the days pointer. We note every write and read, and we note the offsets. After this is done, we can assume that these offsets are offsets for member variables. Now, how about non-virtual functions or simple member functions? We track the disk pointer from the same locations we did with the member variables. The point object is instantiated, the beginning of constructors and beginning of member functions. We note all blocks where ECX is a track variable, then mark the calling that block, if there's any, as a member of the current class. This means that in that block, ECX has the same value as the one that we started tracking. So that means that ECX is a disk pointer, and that function is a member of the current class. The graph that I showed you before, it actually splits per function, so there would only be one function call in a single block. So we're pretty sure here that this call is a member of the function of the class. Now, after member identification, we'll have added member variables and member functions.
Enhancing this assembly. So if you have either Python script or an IDC script, when you parse the BF table and the RTTI complete object locator and other data structures related to RTTI, you can just name them properly. In this example, we had named the BF table and then the RTTI complete object locator, and then set up each field. You just comment it so that when you review the disassembly, you can easily identify what the fields are for.
Okay. So the output of our tool, actually, we generate a pseudo UML diagram, where we create a node for each class and create an edge from each base class to show the relationships. This is very effective if RTTI exists, because we can actually see the actual file class names that were assigned to the classes. So here's an example output without RTTI. So the name what we assigned was something that we generated. But with RTTI, the name is actually what the original name of the class. Okay. So we're going to do a short demo. Actually, we didn't do anything special with in this tool. All the algorithms I mentioned were the only ones we did. We didn't do anything fancy. Okay. So we're going to show. This is a MyTab variant. It'll take a while. Okay. Please be patient. It'll take a while. This tool actually takes a while to run, but the good news is you only have to do it once for every binary. You don't have to do it several times. Okay, so here, this is just a debug output. Okay, once it is done, will generate this graph. Okay. This is MyTop.bi. It's one of the MyTop variants that was coded in C++. Okay, you have to take my word for it, but this class is a threading class, and all the class below it inherits from that class to implement the threading features. And each of these classes implements a specific module: one for registry modification, process termination, and what was it? And internet networking function. But the one application of this tool is if you have a group of reverse engineers and you lack time, you can actually divide the workload among them by modules. So that's one of the possible applications. And you can also name, you can also know what to name all the functions corresponding to the modules that they belong to. So at one glance, you can identify what they do. And it will make the reversing process much faster in some cases. Okay, that's it. Okay, any questions?
Download.
Excuse me?
Download the tool. Basically, the tool we are not allowed to release a tool. So if you'll be doing it, you can just follow the manual instruction and then try to code something in IDC or either Python. So that's the case.
I highly recommend using eDataSQL because it really makes the development process for this kind of tools really easier. There are more details in the paper, so you can look at that. And we're going to give an updated version within 24 hours, I guess.
So
the one
any
in
questions?
the materials is outdated. So, any more
All right.
questions?
Thank you.
Thank you.